So let's have a simple example. Here actually it's there in your book. In this example we have to find what is the probability that it is either on DD1 or on DD2. You see, when we switch on a television, plenty of channels are there, but we can watch one channel at a time. We cannot watch say 2-3 channels simultaneously. So simply here we define two events A and B as A, the TV is on DD1, and B, the television is on DD2. So here A and B are mutually exclusive, and it's given that the probability that it is on DD1 is 1/3, and that for DD2 is 4/30. Now what to find? The probability that it is either on DD1 or on DD2. Now as the events are mutually exclusive, so here P A union B means probability of occurrence of either A or B, and by addition theorem simply write PA plus PB, and we get the result as 25/39. Now before I start the set theoretic approach, let us have some idea about the operations of set. It's known to you. A union B means this is the union of two sets, and A union B denotes the elements, the set of the elements that belong either to A or to B or to both. Examples are there. A is given 1, 3, 4, 5, 6, B equals to 2, 4, 6, 8, and A union B equals to this. That is the set of elements belonging to either A or B or both. And intersection means the set of elements belonging to both A and B. And this is complements of set. If A is a set, then A dash, A bar or AC. So A bar or AC denotes, or this is the set of the elements not belonging or do not belong to A. It's there, example, universal set is defined, and if A is 2, 4, then A dash means set of elements those do not belong to A. And A union A dash, definitely this is the universal set, and A intersection A dash, this is a null set. So these approaches are needed in set theoretic approach of probability. This is the difference of sets. If A equals to the set 1, 3, 4, 5, 6, B equals to this, then A minus B. So what is A minus B? The set of all elements which belong to A but do not belong to B. Venn diagram very often we use in set theoretic approach or in modern approach. A union B, that means the set of elements belonging to either A or B or both, and this is the A intersection B. Similarly, just see these things. I think known to you, all these things. Now this is the beginning of the set theoretic approach that comes under the modern approach. Here actually the events are defined in set. So the first thing you need to know is the sample space. The set of all possible outcomes of a random experiment is known as sample space. The set of all possible outcomes. For example, if I throw a dice, then the sample space will be S equals to the set 1, 2, 3, 4, 5, 6. That means set of all elements, all outcomes. If If I toss a coin, then the sample space will be HT. If I toss two coins, then what will be the sample space? That means how many possible outcomes are there? For first coin, two possible outcomes. For second coin, also two possible outcomes. So when two coins are tossed together, how many possible outcomes will be there? 2 into 2, that is 4. HH means head on first coin, again head on second. HT, head on first coin, tail on second. Now HT and TH different. TH means tail on first coin and head on second coin, and then TT. So these are the four possibilities when two coins are tossed, and the set of all these possibilities is the sample space when two coins are tossed. Now, how to define an event? An event is the set of outcomes of a random experiment. It is simply said that set of outcomes, not necessarily that set of all possible outcomes. The event is a set of outcomes. For example, if I throw a dice, then the sample space is 1, 2, 3, 4, 5, 6. And if I declare an event A as the event of getting an even number, that means A will be the set 2, 4 and 6. So this is also a set of outcomes. Now what is this event A in this dice throwing example? This is nothing but a subset of the sample space A. So any subset of the sample space S is termed as an event. And more particularly, an elementary event is the set which contains a single sample point. A single sample point. Sample point means the elements in the sample space. These are known as the sample points. And you see, as per the definition, as it is said that an event is a subset of the sample space S. Now, S, the sample space, is itself a subset of S, and this sample space is known as the sure event or certain event. And the null set phi is also a subset of the sample space S, and this is known as an impossible event. Now, two events are said to be mutually exclusive. Now, in set theoretic approach, we use this term, mutually disjoint. The meaning remains same, the term differs. In set theoretic approach, we say that mutually disjoint. So, two events are mutually disjoint if A intersection B equals to phi, a null set. For example, in dice throwing experiment, if A denotes the event of even number and B denotes the event of odd number. So in this example, A and B are mutually exclusive. That means A will be the set 2, 4, 6 and B will be the set 1, 3, 5. And what will be A intersection B? This is a null set, no element common. So if two events A and B are there, and if we see that A intersection B equals to 5, then we say that the events are mutually exclusive. Just to go through this example. And this is the axiomatic approach to probability. Axioms means some postulates or rules. And in axiomatic approach, the notion of sample space is incorporated. It is said that let S be a sample space of a random experiment. If to each event A of the set of all possible events S, if to each event A of the sample space S we associate a real number PA, then PA is called the probability of the event A if these three axioms are satisfied. That means if S be the sample space and if A be an event on the sample space S, then PA will be called the probability of the event A if these three conditions are satisfied. Number 1, PA greater than equal to 0. Number 3, PS equals to 1. Sorry, number 2, PS equals to 1. And number 3, if A1, A2 in this way, A1, A2, A3, A4, plenty of events are there, and if these events are mutually exclusive or mutually disjoint, then P A1 union A2 union so on equals to sum of their separate probabilities. So if these three conditions are satisfied, then the function PA is called the probability of occurrence of the event A.